Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of this lecture is Equations of Change for Isothermal Systems. In the previous lecture, we have started discussing about a few basics of transport phenomena. We have discussed transport phenomena at different scales, and then we have studied a few basics of continuum hypothesis, and then we have also seen a few basics of transport by molecular mechanism. In this particular lecture, we are going to discuss derivations of equations of change for isothermal system. So, we start with the derivation of equation of continuity, right. So, here what we do, we take a control volume of size delta x, delta y, delta z, right, and over which we will be doing a kind of mass balance, right. So, this is the control volume we have selected. Horizontal direction is x direction, vertical direction is z direction, and another direction is the y direction. This is how coordinate system we have taken. The size of the element control volume in the x direction is delta x, in the y direction is delta y, and then in the z direction it is delta z. Okay. Now, mass balance over a control volume delta x, delta y, delta z we are going to do, right. So, now here rate of mass accumulation should be equals to the rate of mass in minus rate of mass out. So, mass may be entering in all three directions and then may be leaving all three directions. That generalized one we are going to take now. So, let us say mass that is entering through this shaded phases in x direction at x is equals to x. So, that is nothing but rho Vx at x multiplied by area of the phase through which it is entering. So, area of the phase through which it is entering is nothing but delta y, delta z, right. Similarly, the mass at the rate of mass that is going out in the x direction, but at location x plus delta x, that is nothing but rho Vx at x plus delta x multiplied by the area of the phase through which it is leaving. So, that is the area is nothing but delta y, delta z. Likewise, the rate of mass that is entering in the z direction is nothing but rho Vz at z multiplied by the area of the phase through which it is entering. So, that is nothing but delta x multiplied by delta y. Similarly, the rate of mass that is leaving or going out in the z direction is rho Vz at z plus delta z location multiplied by the area of the phase through which it is leaving, that is nothing but delta y multiplied by delta x. Likewise, in the y direction also the rate of mass that is getting in is rho Vy at y is equals to y multiplied by the area of the plane through which it is entering is delta x, delta z. So, that is this direction here. So, now similarly the rate of mass out leaving at location y plus delta y is nothing but rho Vy at y plus delta y multiplied by the area of the phase through which it is leaving, that is delta x, delta z, right. So, that is what we are doing. So, now the rate of mass in the entire control volume minus rate of mass out in the entire control volume should be, rate of mass in the entire control volume should be addition of the mass in all three direction x, y and z, x, y and z direction. Similarly, rate of mass out in the entire control volume, that is leaving rate of mass leaving out at x plus delta x and then y plus delta y and z plus delta z locations. Okay. So, individually we do and then we combine them together, so that we have the entire net rate of mass flow through the control volume. So, in the x direction if you write, you have rho v x at location x multiplied by delta y delta z minus rho v x at location x plus delta x multiplied by delta y delta z. Similarly, in the y direction, rho v y at location y multiplied by delta x delta z minus rho v y at location y plus delta y multiplied by delta x delta z. Likewise, in the z direction, rho v z at location z multiplied by delta y delta x minus rho v z at location z plus delta z multiplied by delta y delta x. Okay. So, now in the entire control volume, the mass balance is whatever the rate of accumulation is there, that is nothing but dou rho by dou t multiplied by delta x delta y delta z, that should be balanced by the rho v x at x minus rho v x at x plus delta x multiplied by delta y delta z plus rho v y at y minus rho v y at y plus delta y multiplied by delta z delta x plus rho v z at location z minus rho v z at location z plus delta z multiplied by delta y delta x, right. Now, this equation what we do, we divide by delta x delta y delta z both sides, and then applying the limiting conditions of delta x tends to 0, delta y tends to 0, delta z tends to 0, that is the very small size of control volume, and then applying the principles of derivatives, then we get this equation after dividing by delta x delta y delta z, we get this equation after dividing by delta x delta y delta z both sides, and then applying delta x tends to 0, delta y tends to 0, delta z tends to 0, we will be having this equation. Now, this is nothing but minus dou by dou x of rho v x, and this is nothing but minus dou by dou y of rho v y, and this is nothing but minus dou by dou z of rho v z. So, that is dou rho by dou t is equals to minus of dou by dou x rho v x plus dou by dou y rho v y plus dou by dou z rho v z. This is what we have, and this is nothing but the continuity equation. This is the continuity equation that we are going to use extensively in the rest of the course. In vector form, the same equation we can write dou rho by dou t is equals to minus del dot rho v. What does it indicate? Rate of mass, rate of increase or accumulation of mass per unit volume is nothing but the net rate of mass addition per unit volume by convection. That is, continuity equation describe the time rate of change of fluid density at fixed point, Okay. So, del dot rho v is nothing but the divergence of mass flux, that is del is nothing but it indicates the divergence, rho v is nothing but the mass flux, that is divergence of mass flux is the net rate of mass efflux per unit volume, that is what it mean by. And then for a fluid of constant density, we can write the same continuity equation as del dot v is equals to 0, right. So, now this is about the continuity equation derivation in rectangular coordinates. What we can do the same thing in cylindrical coordinates, we can do the same thing in spherical coordinates, and then accordingly we can develop the equation of continuity in cylindrical and spherical coordinates as well. Or otherwise, we whatever the continuity equation that we have derived in rectangular coordinates, we can apply appropriate transformations for r theta z for cylindrical coordinates, and then r theta phi for spherical coordinates, and then do the simplification. Then we get the continuity equation in cylindrical and then spherical coordinates respectively as well. However, we can also do the same thing for any arbitrary irregular shape of control volume as well, and then we can develop the continuity equation also. But however, in such case where the geometry is irregular, the continuity equation we write in a integral form. So, now we are enlisting this continuity equation in rectangular coordinates. Whatever we derived is nothing but dou rho by dou t plus dou by dou x of rho v x plus dou by dou y of rho v y plus dou by dou z of rho v z is equals to 0. Same thing in cylindrical coordinates, if you do, you get dou rho by dou t plus 1 by r dou by dou r rho r v r plus 1 by r dou by dou theta rho v theta plus dou by dou z of rho v z is equals to 0. In spherical coordinates, if you do, you get dou rho by dou t plus 1 by r square dou by dou r of rho r square V r plus 1 by r sin theta dou by dou theta rho V theta sin theta plus 1 by r sin theta dou by dou phi of rho V phi is equals to 0. Okay. So, what is the point of going through this continuity equation is that any flow field that you take and then you try to solve the problem, whether it is theoretically, whether it is just using analytical expressions, analytical approaches or computational approaches, whatever you do, the final flow field the final flow field that you get as a solution, that must satisfy the continuity equation. Then only we can say the solution is reliable if you are doing the solution in microscopic level. Okay. If you are doing the transport phenomena problem at microscopic level and then after solving you get the velocity profile, if that velocity profile is satisfying the continuity equation, then only you can say that the solution is reliable, otherwise you cannot say that your solution is correct. That is the one of the important thing that we are going to keep in mind for the rest of the course, and then whenever we are using these equations to solve the problems, then also we are going to have a kind of a recapitulation of the same information. So, basically the solution for any flow field that you get, whether it is by analytical approach or numerical approach, whatever it is, that solution must satisfy the continuity equation, then only we can say the solution is reliable. Now, we see equation of motion, right. So, now that is momentum equation that we are going to derive, right. So, whatever the momentum equation that you have seen in UG level transport phenomena, primarily that you have derived for Newtonian fluids, and then the momentum equations, corresponding momentum equations are nothing but the Navier-Stokes equation. But now in this course what we do, we will be deriving a momentum equation, very generalized one that can be used for any type of fluid. Okay. However, we apply the limiting condition of Newtonian fluids and then try to get back the Navier-Stokes equations as well. Let us say this is the control volume that we are taking. So, if it is x, y, z location, and then this location is x plus delta x, y plus delta y, z plus delta z. The coordinate system, horizontal direction we have taken x direction, vertical direction we have taken z direction, and the other third direction is the y direction. So, now the size of this control volume, if you see in the x direction it is delta x, in the y direction it is delta y, and then in the z direction it is delta z. Okay. Now, momentum balance over the volume element delta x, delta y, delta z over which fluid is flowing, we are going to take. So, now this element whatever we have taken in a fluid element which is flowing at a particular instant, at particular location. We have taken one fluid element whose volume is delta x, delta y, delta z, that is whose size in the x direction is delta x, y direction is delta y, and then in z direction its size is delta z. Okay. So, now this control volume what we have the momentum is entering, right, momentum is entering and then leaving all 6 phases, that is what we have to understand first. Okay. So, that is what we are going to see. Now, each phase, what is the momentum entering, and then at each phase what is the momentum leaving out, and then we do the balance. So, the balance, if you write for momentum, rate of increase of momentum should be equals to rate of momentum in minus rate of momentum out plus external force on the fluid if at all they are acting, right. Whatever the extra forces are acting, that may be because of the gravitational field, because of the reactions, because of the electric field, because of the magnetic field, whatever the additional terms would be there, all those terms should be coming and then being added up in the right hand side in the balance of momentum equation. Okay. So, since now we are doing from chemical engineering point of view, we take the external force because of the gravity field only we are going to take and then do the equation derivation, right. If at all, as mentioned already, if at all additional terms are there because of the reactions, because of the electric field, or because of the magnetic field, because of the nuclear sources, whatever is there, all those terms should be added up in the right hand side if at all they are existing. So, now what we understand that the fluid is moving through all 6 phases of a volume element, whichever the phase you take. The control volume we have taken cubic control volume. So, all 6 phases through which the fluid is moving. So, what we will be having 3 momentum equations, one in each direction. We are going to have a momentum equation. Continuity equation, we have only one continuity equation if you take rectangular coordinates. If you take cylindrical coordinates, then also one equation. If you take spherical coordinates, then also only one continuity equation is possible. But now here what happens, the momentum that is entering, the fluid is moving through all 6 phases. So, then all 6 phases, momentum may be transferring in different directions, and then different orientations are possible. So, then obviously, if you take the rectangular coordinates, we will be having one momentum equation in x direction, we will be having one momentum equation in y direction, we will be having one momentum equation in z direction, right. So, that is what we are going to have. So, if you have geometry in cylindrical coordinates, then you will be having one momentum equation in r direction, you will be having one equation in theta direction, you will be having one momentum equation in z direction. Likewise, if you are having a control volume in spherical coordinate system, then you will be having one momentum equation in r direction, another equation in theta direction, another equation in phi direction. So, that is possible. Okay. So, now this momentum, whether it is entering or leaving, it may enter and leave either of the two transport mechanisms or both the transport mechanism, depending on the situation to situation. So, what we do, we are doing a generalized case. So, then what we are taking, the momentum whatever is there, that is entering and then leaving because of both the transport mechanism, that is molecular transport mechanism and then convective transport mechanism. So, momentum enters and leaves the control volume by two mechanisms, convective transport and then molecular transport. Okay. So, now we are going to do a balance. The same control volume I have drawn here. Okay. So, this is your x, y, z, this location is x plus delta x, y plus delta y, z plus delta z location. So, now x momentum entering at x location, what it is, right. So, entering because of the molecular transport, entering because of the convective transport, both are possible. So, then what I am writing, momentum flux tensor that I am writing, combined momentum flux tensor that I am writing, that is nothing but phi I am taking, right. Phi in x direction, it is entering at location x multiplied by the area of the phase through which it is entering. So, that is nothing but area of this phase is nothing but delta y delta z. Similarly, the same x momentum leaving in x direction at location x plus delta x. So, that is nothing but phi x x at x plus delta x multiplied by the area of the phase through which it is leaving, that is delta y delta z. Similarly, in the z direction, whatever the x momentum is entering, so that is phi z x, that is entering at location z, and then the area of the plane through which it is entering. So, that is nothing but delta y and then delta x, because this is delta x, this is delta y and then this is nothing but delta z. Okay. the directions are given like this. Similarly, same x momentum leaving at z plus delta z location is nothing but phi zx at z plus delta z multiplied by the area of the phase through which it is leaving, that is nothing but again delta y multiplied by delta x. Likewise, in the y direction, if you take in the y direction, x momentum is entering at y location is nothing but phi y x at y multiplied by the plane through which it is entering, that is delta x delta z. Similarly, x momentum leaving in the y direction is phi y x at y plus delta y multiplied by the area of the phase through which it is leaving, that is delta x delta z. So, the overall x momentum that is entering in all 3 directions and then leaving all 3 directions can be obtained by adding all these components. So, rate at which x component of momentum enters across the shaded phase at x by all mechanisms. So, this shaded phase we have taken is nothing but phi xx at x delta y delta z. The rate at which it is leaving at location x plus delta x is phi xx at x plus delta x multiplied by delta y delta z. Similarly, x momentum entering at location y and then leaving at location y plus delta y are nothing but phi yx at y multiplied by delta z delta x and phi yx at y plus delta y multiplied by delta z delta x. Likewise, rate at which x momentum entering and leaving the phases at z and z plus delta z are nothing but phi zx at z multiplied by delta y delta x and phi zx at z plus delta z multiplied by delta y delta x respectively, right. So, these contributions are added together to get net rate of addition of x momentum. So, that is nothing but phi xx at x minus phi xx at x plus delta x multiplied by delta y delta z plus phi yx at y minus phi yx at y plus delta y multiplied by delta z delta x plus phi zx at z minus phi zx at z plus delta z multiplied by delta x delta y, right. So, this is the net rate of addition of x momentum, it is only x momentum only in the x direction. Okay. So, external force on fluid, now we are taking only gravitational field only and its x component if you wanted to write, that would be nothing but rho gx multiplied by delta x delta y delta z, right. If any additional terms, reaction terms etc. are also there, they are also causing some momentum transport, then additional terms would be there. So, but we are limiting ourselves by including only one external force term, that is because of the gravitational field. Now, rate of increase of x momentum within the volume element is nothing but dou by dou t of rho Vx multiplied by delta x delta y delta z. So, now what we do, these two equations, equation 5 and 6 will be substituting in equation number 1, which is nothing but the overall balance equation, and then we divide by delta x delta y delta z both sides, then we get this equation. So, accumulation term is dou by dou t of rho Vx delta x delta y delta z, that we are dividing by delta x delta y delta z, and then net rate of addition of x momentum is nothing but these 3 terms and then these 3 terms by equation number 5. So, then we are dividing by delta x delta y delta z both sides. So, then here we have, and then external force if any, that we have taken gravitational force. So, rho g x delta y delta z given by equation number 6a divided by the volume of the control volume that we have taken, that is delta x delta y delta z. So, now what we can do, we can cancel out this delta y delta z here. So, delta x is remaining. So, likewise delta s delta x delta z delta x delta z delta x we are cancelling out here also, right. And then we apply the limiting conditions of delta x tends to 0, delta y tends to 0, delta z tends to 0, then we have this equation, that is dou by dou t of rho V x is equals to minus of dou by dou x of phi x x plus dou by dou y of phi y x plus dou by dou z of phi z x plus rho g x. This is what we have. Okay. Now, similarly, y component of equation of motion, if you do the balance and then do the simplification, you will get dou by dou t of rho V y is equals to minus of dou by dou x of phi x y plus dou by dou y of phi y y plus dou by dou z of phi z y plus rho g y. And then likewise, in the z direction, the z component of equation of motion is nothing but dou by dou t rho V z is equals to minus of dou by dou x of phi x z plus dou by dou y of phi y z plus dou by dou z of phi z z plus rho g z. This is what you get. Okay. So, in vector tensor notations, if you wanted to write this equation, you can write dou by dou t of rho V I is equals to minus of del dot phi I plus rho g I, where I can be anything x, y, z. So, it is not one equation, it is representation of 3 equation. If I is equals to x, then it will be giving one equation, that is equation number 7. If I is equals to y, then you will get equation number 8. If I is equals to z, then you get equation number 9. Okay. Now, ith component of equation number 10 is multiplied with a unit vector in ith direction, and all the components are added together vectorially, then we get this equation, generalized equation dou by dou t of rho v is equals to minus of del dot phi plus rho g. Okay, this is what we get, right. This is again generalized form of momentum equation. It is 3 equations, right. Whichever coordinate system you take, it indicates 3 equations. Now, what is phi? Phi is nothing but combined momentum flux tensor, as I mentioned, that includes the contribution because of convective momentum flux as well as the molecular momentum flux, both the terms it includes. Rather, why we have written like this? Because phi is having 2 components, right. Momentum flux because of the convection whatever is there, that is nothing but rho v v, and then momentum flux because of the molecular transport mechanism is nothing but pi, and then that pi is nothing but p Kronecker delta plus tau. That means, we are having phi is equals to this equation, rho v v plus p Kronecker delta plus tau. So, now this we have written whatever the phi x x. If you write for individual components like convective component and then molecular transport component like individually, so then you will be writing 3 terms at each point and then in one direction. So, all the directions you will be having like 3, 3, 6 and then 18 terms you might be writing for x component of momentum equation. Similarly, another 18 for y component of momentum equation, another 18 for z component of momentum equation. That is the reason writing so many terms may be confusing, and then sometimes overlook errors may also lead to the wrong derivation. So, that is the reason we have combined them all of them together as a one part. Now, we have derived actually the equation number 10a, 10b whatever we have written in the previous slide, that is nothing but the complete momentum equation, we derived it actually. Now, what we are going to do, what is this phi, that is we are going to substitute. Okay. So, this we are going to do now. So, now in equation number 10b we are going to substitute whatever this phi information is there. So, equation number 10b is nothing but dou by dou t of rho v is equals to minus del dot phi plus rho g. This is what we have. Now, in place of phi, if you write rho v v p rho v v plus p Kronecker delta plus tau, then we will be having minus del dot rho v v minus del p minus del dot tau plus rho g is as it is. This equation is nothing but Cauchy's momentum equation, and it is a generalized momentum equation. It is valid irrespective of the nature of the fluid, irrespective of the nature of the flow. Okay. For all flow regimes, for all fluids, it is valid. Okay. So, here in this equation, whatever the left hand side term is nothing but the rate of increase of momentum per unit volume, that is temporal term or accumulation term. Then right hand side first term is nothing but the rate of momentum addition by convection, only because of the convective mechanism whatever is there, that term per unit volume. Next two terms are nothing but the rate of momentum addition by molecular transport per unit volume, and then last one is nothing but because of the external force on fluid per unit volume. Okay. So, whatever the possible ways of momentum entering and leaving, including one additional external force, that is gravitational force, all of them are included in this equation. And then again this equation is not one equation, it is a generalized equation. In vectorial form we have written, it is having 3 equations. It is having 3 equations. So, then it is having, it includes x component of momentum equation, y component of momentum equation, and z component of momentum equation as well. That is, if we expand this equation and then write for individual x, y, z components, so then you will get these equations. X component you get rho dou Vx by dou t plus Vx dou Vx by dou x plus Vy dou Vx by dou y plus Vz dou Vx by dou z is equals to minus dou p by dou x minus of dou by dou x tau xx plus dou by dou y tau yx plus dou by dou z tau zx plus rho gx. Right. Now, y component, if you do this again from the equation number 12 only, y component, for y component if you write rho dou Vy by dou t plus Vx dou Vy by dou x plus Vy dou Vy by dou y plus Vz dou Vy by dou z is equals to minus dou p by dou y minus of dou by dou x tau xy plus dou by dou y tau yy plus dou by dou z tau zy plus rho gy. And then likewise z component equation, z component of momentum equation rho dou Vz by dou t plus Vx dou Vz by dou x plus Vy dou Vz by dou y plus Vz dou Vz by dou z is equals to minus dou p by dou z minus of dou by dou x of tau xz plus dou by dou y of tau yz plus dou by dou z of tau zz plus rho gz. Now, these all 3 equations are coming from equation number 12. Equation number 12 is having 3 equations, and then all those 3 equations, if you separate out, you have these 3 equations, right. So, one expected to remember this equation at least in Cartesian coordinates if somebody is working in the area of fluid mechanics or transport phenomena related problems. However, it is not essential, right, because remembering or memorizing these equations in Cartesian coordinates a bit slightly easier compared to the same in spherical and then cylindrical coordinates. However, it is not essential at all these equations are available in standard transport phenomena textbooks, or whenever you need to solve any problem that we are going to do in the subsequent part of the course, this equation would be provided. Okay. Now, this equation, whatever this tau xx, tau yx, tau zx etc. are there, that if you substitute for the Newtonian fluid, then you will get here minus dou p by dou x plus mu dou square Vx by dou x square plus dou square Vx by dou y square plus dou square Vx by dou z square you will be getting. That is nothing but the Navier-Stokes equation. That is what we are going to see. What are these components for a Newton's law of viscosity? That we should have information. So, they are also available in standard textbooks. Tau xx, tau yy, tau zz are normal stress normal are nothing but the normal viscous stresses for the Newtonian fluids, but they are extra stresses for non-Newtonian fluids. Okay. So, what are they, that we have to know. So, let us say if you have a Newton's law of viscosity, then you have this tau expression like this. tau is equals to minus mu del v plus del v transpose plus 2 by 3 mu minus kappa del dot v Kronecker delta, right. If you expand, it is not one equation, it is again, it is having 9 components together, generalized one it is having, in a generalized form it is written. So, we can write all the 9 components individually also. So, we write then tau xx is given by this, tau yy is given by this, tau zz is given by this, and then tau xy is equals to tau yx is equals to this one. So, this is nothing but your del v, this is nothing but del v transpose. Then similarly tau yz is equals to tau zy is equals to this one, and then tau z is equals to tau xz is equals to this one. So, these are equal, we can say, only for a Newton's law of viscosity when it is valid. Okay. And then whatever del dot v in the end is nothing but dou vx by dou x plus dou vy by dou y plus dou vz by dou z. Okay. So, when the fluid is assumed to have a constant density, the term containing del dot v may be omitted, because del dot v is equals to 0 if for a constant viscosity system, that we have already seen from the continuity equation. And then for monoatomic gases at low density, the dilational viscosity kappa is 0 in general. Okay. Then the same momentum equations, let us say if you do the derivation in cylindrical coordinate systems, or whatever the momentum equation just now we derived in rectangular coordinates, and then we apply transformation to get the cylindrical coordinate equation, you will get this following equation. R component of momentum equation is given this one, theta component of momentum equation is given by this one, and then z component of momentum equation is given by this equation. Okay. Here also in cylindrical coordinates, Newton's law of viscosity, if you write, you get all those 9 terms written like this. Okay. And then likewise, if you derive these momentum equations in spherical coordinate system, or whatever the momentum equation just now we derived in Cartesian coordinate system, you apply corresponding transformation to get the spherical coordinate equations, then you will have equations of motion in spherical coordinates like this: r component of momentum equation, theta component of momentum equation, and then phi component of momentum equation, right. So, likewise in spherical coordinates also, Newton's law of viscosity if you apply, then all these components tau r, tau phi, tau theta, etc., you get by this equation, right. All these equations you do not need to memorize, they are available in standard transport phenomena textbooks. Also they will be provided whenever you need to solve any problem in general. So, that is about the momentum equations. Okay. How to derive the momentum equation, that is what we have seen. Okay. Now, what we are going to see is that different types of derivatives in general used in transport phenomena, like partial derivative, total derivative, substantial derivative, etc. What are they? That is also we know. However, we are going to have a kind of recapitulation. Partial time derivative dou by dou t. So, it is something like we take as a kind of fish concentration or number of fishes in a lake. So, you are sitting on the bank, or in a river we are doing, let us say in a river, if you wanted to find out the fish concentration, right. So, you are sitting on the lake, and then you select or choose a position or a fixed coordinate system you choose within the river. You fixed a location, that is nothing but you are taking the fixed coordinate system, spatially fixed location, and then with respect to time you are measuring how many number of fishes are crossing that particular location, and then you are measuring that concentration with respect to time. So, that if you write, you get, that is nothing but your partial time derivative, where you are fixing the location and then variations you are taking only with respect to time. That is, stand on the bank and observe the concentration of fish in the river on a particular location, any fixed location of x, y, z. As function of time you measure that concentration. So, that is nothing but partial time derivative, where one can record time rate of change of fish concentration at fixed location. and this is called partial time derivative of fish concentration at fixed location at fixed xyz of constant xyz coordinate, and then if C is the fish concentration, then partial time derivative of fish concentration is nothing but dou C by dou T at fixed x, y, z coordinates. Location you are fixing the location, and then you are not in the river, right, you are sitting on the bank, and then you are fixing a location in the river, and then you are trying to measure the rate of time rate of change of fish concentration at particular location, and then with respect to time that concentration you are the fish concentration you are measuring. So, that is nothing but dou C by dou T. Okay. Next is the total time derivative. Now, what you do, you understand obviously the fish concentration in the river, entire river is not going to be the dou C by dou T at constant x, y, z. It will not give the true picture, it will give the reliable picture at fixed location only, but if you change the location, the fish concentration may be very different, right. If you go to some other location, the fish concentration may be even further different compared to the second location or first location. Likewise, if you take n number of locations in the fish, you understand the concentration of the fish is going to be very different compared to the fixed location wherever you have taken. That means, if you wanted to represent the fish concentration in the river by partial time derivative, you are going to get a very wrong value that cannot give a true picture. So, now what you do? Next time you take a boat and go around the river, and then go around the river, and then at different locations with respect to time, you try to measure the concentrations. So, now you are in the river, but you are on a boat, and then on the boat you are taking around the river, in different locations you are selecting, and then at different location with respect to time as well as with respect to the space, you are trying to find out the concentration of the fish, because you know that whatever the fish concentration that you representing by partial time derivative is highly inaccurate. So, that is the reason you are doing this one. So, when you do this thing, whatever at any instant the time rate of change of observed fish concentration that you get by total time derivative, that is nothing but dC by dt, that is nothing but dC by dt is equals to dou C by dou T at fixed x, y, z plus dou C by dou x at fixed y, z and time multiplied by dx by dt plus dou C by dou y at fixed x, z and time t multiplied by dy by dt plus dou C by dou z at fixed y, z and time multiplied by dz by dt, right. So, now fish concentration with respect to time by keeping coordinates all x, y, z coordinates, that is already included partial time derivative, plus in addition to that one, fish concentration at different x, y, z locations are also reported by taking corresponding other space and then time variables as constant, and then the multiplication factors dx by dy, dx by dt, dy by dt, dz by dt are coming for all these three terms, and these terms are nothing but dx by dt, dy by dt, dz by dt terms are nothing but the x component of boat velocity, y component of boat velocity and z component of boat velocity at any location, at any fixed location, at any fixed time that you are taking. Okay. So, the components of boat velocity, they are not the river velocity. Obviously, the boat velocity is now you realize that it is very much different compared to the river velocity, right. River velocity at different locations, if you measure the velocity, fluid stream velocity, you may have the different values, right. Different values you will obviously have. You will not be the river velocity would not be the same as the boat velocity, or boat is not moving at the same velocity as the river stream velocity. At different location, river stream is having different velocity, but boat velocity you are controlling mechanically, you are controlling it. You can have higher or lower speed compared to the reverse stream velocity, whatever you want, right. So, obviously this total time derivative, now you realize it is better than the partial time derivative, but still it is not very much reliable, because whatever these velocity components are there, so coming into the picture in this total derivative, these velocity components are not of the reverse stream at different locations, but of the boat, right. So, then that is the reason what you do, you make further improvement by defining substantial time derivative, where you are imagining sitting in a canoe and drifting with river current, right, and then observing the fish concentration, right. Velocity of observer is now same as the velocity of stream with Vx, Vy, Vz components, because now you are sitting in a canoe and then drifting with river currents. You are not changing the velocity, rather you are drifting with the river current velocity, stream whatever the fluid streams there in the river. So, that velocity at different location, that is itself you are taking. So, that means the velocity of observer is now same as the velocity of the river stream, and then that river stream having Vx, Vy, Vz components at each location, Okay. Thus, time rate of change of fish concentration can be written as capital dC by capital dt is equals to dou c by dou t. This again partial derivative is coming into the picture, plus Vx dou c by dou x plus Vy dou c by dou y plus Vz dou c by dou z, right. So, now here when you measure dou c by dou x, obviously y, z and t are constant, and then here also dou c by dou y when you measure, so z, x and t are constant, and then here also when you measure dou c by dou z, you keep x, y and t as constants, right. So, these Vx, Vy, Vz are nothing but the components of the velocity of the stream. So, the same equation 14a, if you write in vectorial form, you have capital dC by capital dt is equals to dou c by dou t plus v dot del c. That means, whatever capital D by dt, that is nothing but dou by dt plus v dot del is there, that is called as substantial time derivative, because it also moves with the substance. Now, here the moving substance in the case of river example is nothing but the the velocity of the river streams, right. So, the substantial derivative reports the time rate of change as one moves with the substance. That is the reason it is called as substantial derivative, because it moves with the time. It is also known as the material derivative, hydrodynamic derivative, because it also includes the hydrodynamics of the flowing system, and then derivative following the motion, that is also the other terms are given, different terminologies are there, but the terminology substantial time derivative is famously used. So, that is about the partial, total and then substantial time derivatives, right. Now, we are going to write the so called equations of continuity and then momentum that we have derived in a few slides before. Those equations we are going to write by using substantial derivatives. So, that if you write equation of continuity, you can write capital d rho by dt is equals to minus rho del dot v, whereas the equation of motion you can write rho dv by dt is equals to minus del p minus del dot tau plus rho g you can write. Okay. So, now some simplifications of equation of motion that we are going to see. First one, we take constant density and then viscosity system for Newtonian fluids. That if you do, that is Newton's law of viscosity that you apply, that is in place of tau xx you write minus mu dou Vx by dou x, all those terms, and then simplify, then you will get this equation. Rho capital dV by dt is equals to minus del p plus mu del square v plus rho g. Let us say if you combine this small p and then rho g, rho capital dV by dt is equals to minus del p plus mu del square v, where capital P is nothing but p plus rho g. This equation is nothing but your Navier-Stokes equation. Let us say x component of this Navier-Stokes equation, if you write, you will get rho dou Vx by dou t plus Vx dou Vx by dou x plus Vy dou Vx by dou y plus Vz dou Vx by dou z is equals to minus dou p by dou x plus mu dou square Vx by dou x square plus dou square Vx by dou y square plus dou square Vx by dou z square. This is what x component of momentum equation for Newtonian fluids, which is also known as the Navier-Stokes equation, x component. Similarly, y component and z component also we can write. This you are getting simply in place of tau, you are using this expression and then simplifying it. Now, when acceleration term is neglected in Navier-Stokes equation, that is convective terms, if you take off, then that is whatever the transport is there, the transport is there only because of the molecular transport, then we have the equation 0 is equals to minus del p plus mu del square v plus rho g, which is also known as the Stokes flow or creeping flow equation. Because when there is no convection term, altogether left hand side terms can be taken as 0. This equation is important in some examples like lubrication theory, study of particle motion in suspensions, flow through porous media, etc. Now, another simplification or limitation of a momentum equation, if you take, where the viscous forces are neglected, that is inviscid flows, then we have rho capital dV by dt is equals to minus del p plus rho g. Here whatever the viscous terms mu del square v is there, that term is absent. So, this is known as the Euler's equation for inviscid flow. In fact, there are no true inviscid flows in general, but there are many flows in which viscous forces are relatively unimportant or maybe very small compared to the convection and then other terms, so that those viscous forces can be neglected in many cases. Some of them are flow around airplane wings, flow of river around upstream surfaces of bridge, some problems in compressible gas dynamics, and then flow of ocean currents, etc. So, this is what the recapitulation that we have in this class. Recapitulation, because all these equations are known to you in your UG level transport phenomena course. Maybe these equations are known only for the case of Newtonian fluids case. Now, in this lecture we have derived them for a generalized case, irrespective of the nature of the fluid, irrespective of the nature of the flow, whether laminar, turbulent, Newtonian, non-Newtonian, no restrictions, very generalized Cauchy's momentum equations we have derived here. Okay. The references, all these derivations and then simplifications you can find out in this book Transport Phenomena by Bird, Stewart and Lightfoot. However, similar information may also be found in the Analysis of Transport Phenomena by Dean, or in the book Incompressible Flow by Panton, and then these two are the other reference books which may be useful. Thank you.